AI reasoning engines are scaling rapidly, but their usefulness is bottlenecked by a mechanical problem. They need a way to connect to external tools. If you have M different AI models and N external tools, integrating them requires writing custom connection logic for every single unique pairing. 5 AI apps connecting to 20 tools creates a tangled web of 100 custom connections. Developers must repeatedly rewrite brittle logic for every combination, trapping critical enterprise systems like local file systems and cloud databases behind a massive integration wall. Building highly capable AI agents no longer depends solely on training smarter models. It requires resolving an unmaintainable networking architecture. The Model Context Protocol, or MCP, is an open standard engineered specifically to eliminate these ad hoc integrations. Instead of point-to-point connections, MCP introduces a central standard layer sitting directly between models and tools. It functions like the physical standardization of USB-C, a single universal port replacing dozens of device-specific cables. For developers, this means an external tool only needs to expose itself once as an MCP server. The moment it does, any MCP-compatible AI client can instantly connect to it. By converting an exponential M times N problem into a linear M plus N reality, MCP directly accelerates how autonomous agents interact with their environment. To understand how MCP operates, we first have to draw a strict boundary between the AI's internal processes and the outside world, as shown in this architecture model. Inside that boundary is the host. This is the user-facing application running the AI reasoning engine, like an IDE or a custom desktop assistant. Also inside the boundary is the client. It lives entirely inside the host application to manage all outgoing communication over standard transports. Across the boundary is the server. This is a completely separate service, acting as the external capability provider, exposing data and tools back to the AI. The clients and servers communicate across this boundary strictly through standardized JSON RPC 2.0 messages. Standardizing the message format via JSON RPC ensures the AI's complex internal logic is fully decoupled from the execution of external tasks. When an AI client connects, this blueprint outlines what an MCP server actually offers: 3 distinct capabilities that give the model context and agency. The first are tools. These are specific, executable functions, like search files, that the AI can trigger to perform controlled work in external systems. The second are resources. This is static data or contextual information that the AI can read and ingest without needing to trigger an action. The third are prompts. These are reusable instruction templates that standardize how the AI should behave during repeated workflows. By combining tools, resources, and prompts, an MCP server provides what an isolated reasoning engine needs to systematically comprehend and manipulate an external environment. We can frame this strict separation of capabilities using the operational logic of a commercial restaurant. Here, the AI host acts as the customer-facing waiter. It interprets ambiguous user needs and formats them into a structured request. Notice that the waiter never physically rummages through the pantry or attempts to cook the meal themselves. Instead, the MCP server acts as the back-of-house kitchen. It receives the structured ticket, performs the controlled operation safely, and hands back the result. The rule is absolute. The model is strictly for reasoning, and the MCP server is strictly for controlled capability. The 2 roles must never overlap. Translating that restaurant logic into an engineering algorithm gives us the formal execution loop for an autonomous agent. This equation defines the central mechanism, R equals S of T A. The result equals the server running a requested tool with specific arguments. Looking at the loop diagram, the agent receives the resulting observation, updates its internal state, and then decides its next chosen action within the cycle. To apply this, imagine a user asks an AI to summarize specific biology notes on enzymes. This sequence chart outlines the exact steps. First, the AI decides it needs context. It instructs the MCP client to call the search_notes tool for the term enzymes. The server returns a specific note ID. The AI loop then triggers a second call, fetchNote, to retrieve the full text, which it finally synthesizes into a summary. The AI is not magically guessing information. It is reliably orchestrating standard retrieval patterns through a formal protocol. Exposing real-world data and executable code paths directly to autonomous agents without strict boundaries is an incredibly dangerous vulnerability. A fully functional server remains a massive liability if it fails to implement strict security boundaries. This pipeline shows the 7 steps required to run a minimal server, moving from starting the process on the left to returning structured output on the right. Step 4 is the most critical point of failure in the entire system: validating arguments. Developers must never blindly trust the JSON payload generated by a large language model. Models can easily hallucinate non-existent parameters or execute malicious prompt injections. Securing an MCP server relies entirely on the principle of least privilege, granting the server only the minimal absolute powers required to run its specific tools. Experienced developers often question why MCP is necessary when standard REST APIs already exist. This table contrasts the interfaces. Normal APIs require humans to read documentation. MCP uses JSON RPC, making tools self-discoverable by AI. MCP doesn't replace standard APIs, it wraps them, translating arbitrary endpoints into a format agents can systematically execute. Another major misconception is the belief that MCP is just a rebranded version of traditional function calling. This comparison shows traditional function calling is an app-specific approach, tightly tied to a single host application, giving it very low reusability. MCP is a completely decoupled architecture. It acts as a cross-application standard built to be shared across compatible AI clients. By deploying remote MCP servers, enterprise teams can build one highly secure capability provider and point dozens of different AI tools at it simultaneously. The Model Context Protocol is the definitive, standardized bridge required to safely move AI agents from isolated sandboxes into the complexities of the real world.